Today, I want to talk about solutions and solubility. And I'm going to begin by complaining. Here's a problem I have. You might share it. Have you ever found yourself stirring and stirring sugar into iced tea, but the sugar just remains at the bottom? Well, if you've ever experienced this, you might be looking at a saturated solution. And that's the first idea I want to explore today, this idea of saturation. There's just a limit to the amount of solute a given amount of solvent can hold at a given temperature. You can't put infinite amounts of solute. And a solution that contains the maximum amount of solute as it can hold at a given temperature is said to be saturated. Additional solute won't dissolve in a saturated solution. Undissolved solute will remain at the bottom of the container. And the presence of undissolved solute is a really good indication that the solution is saturated. A solution that has not reached the limit of how much solute it can hold is said to be unsaturated. And additional solute will continue to dissolve in this kind of solution. You can go beyond saturation, though. Under certain circumstances, excess solute can dissolve in solution, despite having exceeded the saturation point. We'll talk a little bit about how you would do that in class. But if you can oversaturate a solution, what you call that is a super saturated solution. And these are highly unstable. Excess solute will undissolve or precipitate or crash out of the solution with very little input of energy. So here's a video of something called sodium acetate that is just chilling out here. And then all of a sudden someone adds a little crystal and then causes all of it to precipitate right out. And it happens super quickly. So it's possible to supersaturate a solution, but it likes to get out. If you've ever made rock candy when you were a kid, that's essentially what you do. You make a supersaturated solution of sugar water, you put a little string in, and the sugar will crystallize on the string, and that's what rock candy is. Solubility of a solution is just the amount of solute that will dissolve under a set of given conditions. So it's a quantifiable number. We usually measure that in grams per milliliter. Factors that affect solubility include temperature, pressure, and the identity of the solute and the solvent. So let's look at temperature. As a rule, as temperature increases, solubility of liquids and solids increases. The higher the temperature, therefore, the more salt can dissolve in water. I hope that makes sense. Here is a graph that you're going to use a lot and get to know. This is a solubility curve, and it shows a lot of data, but what it really has is for a bunch of different ionic compounds, it graphs the amount of grams you can dissolve in 100 grams of water at different temperatures. So for instance, if we look at calcium chloride at 10 degrees Celsius, it looks like we can dissolve about 63, 64 grams of salt in 100 grams of water. At 20 degrees Celsius, it looks like we can dissolve about 76 grams of calcium chloride in water. We can do the same with lead nitrate. At 10 degrees Celsius, we can dissolve 46-ish grams of lead nitrate in 100 grams of water. At 20 degrees Celsius, we can dissolve about 56, 57 grams of lead nitrate in water. It says grams of salts here on the y-axis, and I want to remind you that a salt is really any ionic compound because it's just a compound made of a metal plus a nonmetal. So sodium chloride is the most well-known salt, but all of these things are salts. Let's contrast that with this graph. If you look at the one on the left for just about everything, as we go left to right, in other words, as temperature goes up, solubility goes up. The only weird exception is cesium sulfate over here, where it actually goes down. By contrast, all of these compounds see that as we increase temperature, solubility decreases. And why might those be? Well, if you look at what all these things have in common, they're all gases. It turns out that as temperature increases, solubility of a gas decreases. Because increasing temperature of a gas in a liquid solution results in increased motion of gas particles. The gas particles will collide and combine with each other more frequently, leading to bubbles that undissolve. Think about soda. Soda is a solution of carbon dioxide in water, essentially. And as it gets warmer, you can't dissolve as much carbon dioxide. And that's why warm soda is generally pretty flat, not a lot of CO2. So for solids and liquids, as temperature goes up, generally solubility goes up. For gases, as temperature goes up, solubility generally goes down. Pressure also affects solubility. It does not affect the solubility of solids or liquids. However, gas solubility does increase significantly with pressure. At a given pressure, the sum amount of gas will continually dissolve in a solution, while an equal amount will continually leave the solution. And if we increase the pressure, that will lead to an increase in the dissolution of gas. And after a time, the system will reach a new state of equilibrium. So I've demonstrated that in pictures here. I initially have some gas particles entering and leaving the liquid. If I increase the pressure by pushing down the container, we're going to see more gas particles enter the solution than leave, and eventually we'll see that balance out. So there's going to be a new equilibrium. You've definitely seen impacts of pressure on gas dissolvability. A classic one is when you open a can, bottle, what have you, of soda, you reduce the pressure as soon as you open it, and therefore the gas leaves the solution. You hear a kind of fizz. A worse example in terms of human health is if you're diving, it turns out that people get injured really badly if they leave the water too quickly. In other words, if they come to the surface too quickly. And that's because as you go up, the pressure on you decreases. And that causes some of the gas that's dissolved in your blood to come out of solution. And if that happens too quickly, you get a disease called the bends. It can be pretty bad. It can be fatal. Like dissolves like is a really classic idea in solubility. And it really is a good answer to determine whether or not a solute will dissolve in a solvent. Polar solvents will dissolve polar solutes, and non-polar solvents will dissolve non-polar solutes. Remember, polar just means a molecule that has a distinctive positive and negative side. So we talked about water as being a polar molecule in the last video. All ionic compounds are polar because they're made up of positive and negative charges. Some molecular compounds are also polar. So remember, I talked about dissolving sucrose in water. Sucrose dissolves because it is polar. Many molecules that are molecular may be polar. Here is a listing of polar molecular solvents and non-polar solvents. So we see water, methanol, ethanol, isopropyl alcohol, acetone, and acetic acid, aka vinegar. These are all molecular compounds that are polar, and so they will dissolve polar solutes. And then here are non-polar solvents like hexane, heptane, octane. These are essentially things that you found in gasoline, carbon tetrachloride, oils, greases, waxes. Those are non-polar. So if you remember last video, I talked about oil and water being immiscible. In other words, you can't dissolve them in each other. That's because water is polar and oil is nonpolar. Let's do a little bit of practice using a solubility curve. So we'll start with a simple problem. What's the solubility of NaCl, sodium chloride, at 40 degrees Celsius? So I've drawn here 40 degrees Celsius up to where it hits the sodium chloride line, and we see that it is around 35, 36, 37 grams per 100 milliliters. So the solubility is 0.37 grams per milliliter. We can get a little harder. We can ask, what mass of KClO3 will dissolve in 200 grams of water at 70 degrees Celsius? Okay, well, first let's find where 70 degrees Celsius hits KClO3. It's right around 30 grams per 100 grams of H2O. So I use that to write a ratio. If 30 grams dissolves in 100 grams of H2O, how many will dissolve in 200 grams of H2O? I cross multiply and I get 60 grams. Finally, I can ask a question like this. Is a solution containing 100 grams of water and 40 grams of KNO3 at 50 degrees Celsius saturated, unsaturated, or supersaturated? Well, once again, I will find where 50 degrees Celsius is on KNO3. I find that I can dissolve about, is that like 87 grams? So that's telling me if I can dissolve up to 87 grams at 50 degrees Celsius, then if I only put 40 grams, then that's going to be an unsaturated solution, because as I've just written down, at 50 degrees Celsius, the saturation point is 87 grams per liter. And therefore, this is less than that, and the solution is unsaturated. Last idea is that rate of dissolving, or rate of solvation, is how quickly a solute will dissolve in a solvent, and it's not the same thing as solubility. That's how much will dissolve. Rate is how fast it dissolves. And I just want you to know that there are some things that affect the rate of solvation. Those are surface area. So the smaller the surface area, quicker things dissolve. That's why sugar crystals dissolve faster than big sugar cubes. The number of collisions increases between the solute and solvent with increasing surface area. Agitation, so like stirring, adds kinetic energy, which increases collisions, which increases the rate of solvation. And finally, temperature. At a higher temperature, the particles are moving faster, so there's more motion and collisions. Notice that temperature increases both the rate of dissolving and also the amount that you can dissolve. The other two, surface area and agitation, just increase the rates.